She's from Cambridge. I think we all know her. Take it away. Thank you, Ale.
I'll take it away. So thank you for the invitation. This is a bit of a weird invitation because I was involved in the organization of these meetings. So it's all invited. It's all Pedro's fault and Nico and Al and like all of them. But in any case, I'm very, very happy to be here. I'm very happy to be part of the first of these meetings that is in person. And I hope there's many more in the future. Now, in this room, there's some familiar faces, but most of you, I have no idea who you are. So before we start with the physics, I would like to know, who am I talking to? Because this is a service to you, not to me. And so let me just start asking a few basic questions. So how many of you are bachelor students? Licenciatura, or yeah. Any bachelor students? Don't be shy. No? 0. Okay. Master students. Good. Okay. PhD students. The vast majority PhD students. Will you say that you're in the first half of your PhD or second? First, how many of you are in the beginning your PhD, like first 2 years? Okay. And how many of you are getting close to that scary moment where you have to apply for postdocs and stuff? No? Okay. Good. And how many postdocs? Okay. And above postdocs? At least 2 things. Okay. Great. Good. Next question. Because as you can see from the title of the lectures, I'm going to be talking about ADS-CFT. So who here in the room is actively working or has worked in the past on a topic that relates to ADS-CFT? So you would say that you feel comfortable with ADS-CFT. How many of you feel comfortable with ADS-CFT? That if you say that you know more than, oh, it's something that relates some theory in ADS to some theory in CFT. Raise your hands if you don't feel comfortable with ADS-CFT. That's also very useful for me. So again, so how many of you feel comfortable with ADS-CFT? Feel like, yes, this is okay. Okay, I think like about a third-ish, because I saw like some like, like I read Magoo. Okay. That should already be a lot. How many of you have worked with 3D gravity? Very few, very few. So most of you have not any experience with ADS3 gravity. Great, so that's what we're going to do. We're going to learn about this version of the correspondence. And the reason why I could have given lectures on like ADS-CFT. Like I could have done this for any D+1 and D dimensions, but I like this number of dimensions. I like ADS3 CFT2 because something that I'm kind of unsure about, and part of my research, what I'm trying to understand, is really what is quantum gravity. And what I want to illustrate is that in this instance of the correspondence, historically it's been thought that it's going to be the case that we're going to solve first. Spoiler, it has not been solved. I still don't know what quantum gravity is. But there's a lot of interesting challenges and puzzles that show up in the quest of trying to understand what quantum gravity is. Some of those lessons will extend to higher dimensions, some of them not. But I find it very compelling as trying to kind of get a more in-depth understanding of what is quantum gravity? What are the principles of quantum gravity? How does it work? Why is it so different from other quantum field theories that we think that we're so good at? Okay, so I want to illustrate that. I want to illustrate the paradigms and illustrate those questions. But there will be a lot of questions. And sometimes there will be answers, but a lot of times, depending on which questions you ask me, I won't have the answers. But we'll go through that exercise. And this number of dimensions is great to kind of have an understanding of what's going on. So from that point of view, what I'm going to do, given that very few people raised their hand on like working on 3D gravity, the first part of the lectures is just going to be kind of a review on classical aspects of ADS3 gravity, okay? Depending on how many questions you have, depending if I'm going too fast or if I'm going too slow, you will dictate that pace, okay? So I'm not going to promise you how many lectures we're going to spend on this. You will tell me how many lectures we spend on this. It doesn't matter if I don't get to the end. It's fine. We're having fun. We're in Brazil, right? We'll just drink piña coladas and talk about quantum gravity. Okay, so, but we'll start with the classical part because there's many things there that are interesting, that are new. They will touch also, I was very happy that many of the things that Chiara mentioned in her lecture, we'll see a version of that in 3D, the problem sessions as well, so that will be a good connections with the other lectures. Then I'll make your head spin with quantum aspects of 3D gravity, okay, so to state some older results. And then at the end, I hope I get to this part where here I'm writing, I didn't write ADS-CFT because the perspective that I'm taking, well, and that many people in the field are taking nowadays, I want to see the conformal field theory as a definition of quantum gravity. So it's basically, I want to present to you and to think about how do I manage, organize, put constraints, and understand conformal field theory such that I see the emergence of geometry. Okay, because conformal field theories, if you open the big yellow book, how many of you know about the big yellow book? Many of you? Great. Okay, so if you open the big yellow book, you will not see the word gravity or general relativity, nowhere there. So a lot of the task of the correspondence is trying to understand, like, how do you see gravity show up from this side? Okay, so we'll go through that thought that, again, it hasn't been fully resolved. There's many interesting open questions, but this is where I want to inspire you to think more about this, okay? And so what is this fundamental mechanism? So, okay, so we'll start with the classical part. And again, interrupt me at any point. And what we're going to do is that we're going to study basically the simplest theory of gravity that we can write down in ADS, which is what we call usually pure gravity. So it has this action principle. So here is what I wrote down, what the action of what we call, so the jargon in the field is to call this pure ADS3 gravity. Okay, so just a theory where the metric is the only degree of freedom, and you write it, it's the simplest theory with a two derivative equations of motions, okay? So that's a theory that we're going to obsess with. Of course, you can do more things. You can add matter to this theory. You can add higher derivative corrections. There's many things, but this is the theory that we're going to study. Now, what is known about this theory? And so, and here, just to relate to the notation, for now, I'll keep G. I will set G equal to 1 very soon. L, I think I'm never going to set to 1, but maybe. And this is just in regards to the notation that Chiara was using. The cosmological constant there is negative minus 1 over L squared, where L is a constant. Okay. So what are things when someone says 3D gravity? What do you know about it? I know many of you didn't raise your hand, so probably you know nothing, but maybe, I don't know. Is there something that you know about 3D gravity? What is some cliche, something that the cool kids say at the... There's what, sorry? It doesn't propagate. Why?
Because all degrees of freedom are gauged.
Why?
Because if you try to fix TT gauge, everything happens. You can always go to
Why? That you're saying all true things. And anyone else? Do you know why 3D gravity has no local degrees of freedom? That's very similar to what he was saying. Yeah. Why can you do that in 3D? That's one way how you can discover. So we have made the statement that there's no local degrees of freedom, and it can be cast as a Chern-Simons theory, which is also a topological field theory. So then you can say, like, this is how I discovered that it was a topological theory. But there's a simpler reason. Anyone? Well, yeah, it's going to be, the reason is going to be that it's in low dimension. Who wants to go first? You're super close. Don't go that far. You're going a little bit too far because you're imposing the equations of motions. But I think the same thing? Okay, so the reason is that the Weyl tensor vanishes as an identity. So the reason why all of you guys say this and why then the counting works is because if you open Carroll or any book in GR, one of the first things that you do with the Riemann tensor is count how many number of independent components it has, right? And if you go, so you can look at two things. You can look at the Riemann tensor, and then you can also look at the Weyl tensor. Do you guys know what the Weyl tensor is? Yes? Okay, if you don't, it's the Riemann tensor, but you remove all of the traces. So it's like the traceless version. Should I write well, somewhere there's a definition. But basically, what's happening here, and it's all combined, is that the Weyl tensor vanishes in 3 dimensions. Now, this has nothing to do with this action principle that I wrote. This is just an identity. So it has nothing to do with the specific theory that I have in mind. It is just by counting the number of symmetries that the Riemann tensor has as a definition, that then you go and see how many components the Weyl tensor has, and it has 0 independent component. Therefore, this tensor identically vanishes. So then that tells us, so the consequence from here, and that's very similar to what that gentleman was saying there, is that then if you write down the Riemann tensor in 3D, you can always write it plus I hope I got all the signs correct. But the Riemann tensor in 3D, you can always write it as a function of the Ricci tensor and the Ricci scalar. In any other number of dimensions, you will still have this components here with numerical factors. There's factors of the dimensions that go here. So I already put that d is equal to 3. But then you have the addition of the Weyl tensor on this other side. And the Weyl tensor is usually the quantity that contains the gravitational, the graviton, like the gravitational waves. Okay? So those are part of the Weyl tensor. And so that's also why usually when people do linearized gravity, when they construct gauge invariant versions of gravity waves, they use the components of the Weyl tensor as the gauge invariant definition of what the graviton is. But if the Weyl tensor doesn't exist, then there's no graviton to be talked about, okay? So it's this. And then, of course, the arguments that you were giving about the counting and stuff like that, then it's basically, then you just see like, oh, of course, I could have gauged everything away. There's no local degrees of freedom. Okay? But this is basically an identity. And then, if you impose now the equations of motion, so the equations of motions that come from that action are quite simple. So these are the equations of motions, which of course you can infer from here that r is equal to 6 times lambda, or r is equal to 2 times lambda times, r mu nu, equal to 2 times g mu nu. So then basically what the equations of motions do, they fix for you the Ricci scalar, and then they fix the Ricci tensor, okay? Which is the familiar statement in any number of dimensions. And so then when you replace this in here, then if you're on shell, so if you're satisfying the equations of motion, the Riemann tensor is completely fixed by the metric. So you specify a metric, and it specifies the curvature. Okay? So there you go. There's no local degrees of freedom. So what does this equation then tell us? In terms of like the classical solutions to the equations of motion. Nothing. So what this tells us is that this color is a little bit annoying to write. All the solutions to the equations of motions are locally maximally symmetric. So this is the Riemann tensor. If you, again, open Carroll and see what are the, if you have a space-time that is maximally symmetric, what is the form of the Riemann tensor in any given number of dimensions, you will get an expression with this, with a different normalization up here, but that's not important. And so basically the conclusion is that all solutions to the equations of motions are locally maximally symmetric. What is the maximally symmetric space in this case? It's just ADS3. That's a maximally symmetric space-time with a negative cosmological constant. Okay, we're done. We solved the equations of motions. You perhaps once heard that it was very difficult to solve Einstein's equations. Piece of cake. Just did it. How much time did it pass? 15 minutes. Solved. We're done. Anything else interesting to say about 3D gravity? So this is just a statement that you can make. I'm not lying to you. I'm not cheating. We solved the equations of motions. We are done. But of course, I have to keep on talking for like about another hour. And so what else am I going to say about classical gravity? Okay? For many years, for many decades, for a very, 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 very long time, this was it. For so many decades, nobody looked at lower dimensional cases of the Einstein's equations because in 2D, there's even a more dramatic version of this that even makes the theory even more trivial. And nobody cared about low D gravity. But now we do, so why do we? You know. No, you don't. No? Okay. Tell me. So maximally, like, okay, so this is where I'm going to start refining what I mean. So here, I wrote the word locally. So this tells me that locally, the Riemann tensor is of that form. Now, if you ask globally, from the point of view of a whole manifold of the variety, what is the maximally symmetric space? It is what we will call, and I'll write in a moment, what we call global ADS3. So that's the maximally symmetric solution from a global perspective. So what I'm going to do during the rest of this lecture is kind of harp on this. That this is just telling me something about the local properties of the solutions, but it's not telling me about the global properties of the solutions. So this is one example that, of course, ADS3 is locally maximally symmetric, but it's also globally maximally symmetric. So then the question is, are there other three manifolds that perhaps are locally maximally symmetric, but not globally maximally symmetric? Sorry, yeah. Right. Okay? So now we have to think, okay? So the way that we're going to think about this problem and this is a strategy that is useful not just in 3 dimensions, but it's also useful in other areas of life. But it's something that you really, really like. If you don't think about this in 3D gravity, then you go, after this, you just go home and watch some TV. I don't know. So we're not going to do that. And so the strategy that I want to basically present to you is to, what we're going to do first, so there's going to be 2 things going on here, okay? So there's going to be an issue of, so the way that we're going to try to solve this problem as a start is that we're going to look at boundary conditions. We're going to think in terms of like observables. And in this context, my observables are going to be conserved charges. And then we're also going to think about global properties. So basically think a bit about topology. Okay, which the Einstein's equations don't tell you anything about. So that's something that you have to input by hand, okay? And what this is going to do as an outcome is that we'll see that we'll have 2 types of solutions. We'll have solutions that I'll call perturbative. And we'll have solutions that are non-perturbative. Yeah, just non-perturbative. Okay? So this is what's going to happen to you. And the exercise, the thing that I want you to remember from this is basically these points. As you're confronted with a theory, you need to think about how you're going to organize your quantities. So even the same thing like that Chiara was doing, like she wrote down for you a metric that depended on some parameters, m, q, and lambda, but then, okay, then you can just go. The Rice-Nostrum solution in ADS4 was known like for ages. But then you have to understand, oh, how do you define good boundary conditions? That was her choice of ensembles. And then what were observables that are interesting to compute? The entropy, the free energy. And then you go and see, this is the physics. And you see where the input is. So we're going to do basically a very similar exercise, catered to the case of ADS3, but it's basically that type of mentality, okay? So what are we going to hold fix? How are we going to characterize the space of solutions with that data fix? And what is the quantity that is going to basically, we're going to measure here? What is our observable? Which in physics is crucial, okay? And because there's so much gauge symmetry, we have to be very careful about how we define observables, okay? Very good. Are we ready then? I'll start implementing the strategy. I guess this eraser, yeah, it's kind of. Okay. Very good. So we'll start with this issue. I think there's different ways how I've done this in the past, but I think for today, I decided that the way I wanted to present this was by first talking about this issue of boundary conditions and observables. So I'll basically be starting, which is more natural to do from the point of view of the perturbative. Did I just call them perturbative? Yeah, just call them perturbative solutions in ADS3. Okay, and then we'll get to the non-perturbative ones in a moment. Okay, so the first thing I have to do is, okay, let's write down, so I made a statement there that the solution that we had was just ADS3. So let's just write down such that we're all in the same let's just consider what we call global ADS3. Okay, so what is this maximally symmetric space? So there's a few ways how to define it and write it. You can define it as a hyperboloid embedded in a higher dimensional space. There's many things that you can do, but I'm just going to write it in a few coordinate systems that I like. And so this is a very natural coordinate system for global ADS3. And in this coordinate system, what's important is that phi is identified with 2 pi. Time runs from minus infinity to plus infinity, as expected, and the radius goes from 0 to infinity. Okay, so that's global ADS3. We can also write it, I also like to write it in a different set of coordinates. So this is also a very useful parametrization of ADS3, where the only thing I've done here, I basically transformed R into sinh of rho, and then it was convenient to also redefine time by this ADS radius L, okay? But what's convenient, you can see it, okay, it doesn't matter too much how you do it. You can view it from the point of view of these coordinates or these other ones, but usually the picture, if you wanted to visualize this manifold, if you wanted to have an idea of like, how do I draw ADS3? Basically what, for instance, from this picture, what you're seeing is like, okay, so you have a coordinate that is periodic, phi. There's time that goes from plus to minus infinity. And then the radial direction just basically fills this, this cylinder. So global ADS3 is basically a solid cylinder in terms of a topology. Okay? So topologically, it's the same as a solid cylinder. So quite simple. The sense from which it's maximally symmetric it's because it has, do you want to guess how many killing vectors? So when we talk about symmetries of a manifold, how many killing vectors would a maximally symmetric three-dimensional manifold will have? 6. So it has 6 killing vectors. Killing vectors usually, well, they have to, they form a Lie algebra. And the corresponding Lie algebra, you can write it as 2 copies of SL2. Well, just let me write. So you have 3 for each SL2 as a algebra has 3 generators, so that 3 plus 3 is equal to 6. Or you can also describe it SL2, 2, if I get it correct. I always get this wrong. Yeah. Okay. So that's what shows to you, this is indeed maximally symmetric. It's the maximal number of killing vectors that you can have in 3 dimensions. And you can construct them and see that the killing vectors are globally defined in the entire geometry. This makes the space maximally symmetric. Okay, so that's a very, very explicit, and of course, it will comply with all of this. So R will be equal to 6 times lambda, the Ricci tensor, all of those things are satisfied for that manifold. Okay? Good. Now, it's also convenient. I don't think I'll use it too much. No, I think I'm not going to. Okay. Let me. Let's write it. Okay. So there's also another version of ADS3, which is not in global coordinates. It's what's called like in Poincare coordinates. So, oh, and by the way, okay, so maybe, yeah, sorry, I'm rambling now. So this space-time here is Lorentzian, as I've written it. If you wanted to go to Euclidean ADS3, you just take t to it. Okay, so then you just put a plus there, and that makes it Euclidean. Okay, so what I'm going to do now also, it's also convenient sometimes to introduce a ADS3 in what's called Poincare coordinates. So the metric is much shorter, and there's a factor here outside of L squared. Okay, so that's ADS3 in Poincare coordinates, much less space. But what's nice about this, I just wanted to make a connection with the maximal symmetry, is that this metric, you can write it in this form, where G is a 2x2 matrix that has the coordinate in this way. So you grab G, you take dg of it, you take the inverse, take that trace, it will give you this line element. But what this illustrates, this makes very explicit the reason why it's nice to write it like this. In some ways, you might think it's an overkill, but it has the advantage that you can check the determinant of this metric is equal to 1. And so this metric lives in SL2C. SL2C is basically the Euclidean version of SL2, So when I write Euclidean ADS3, then the gauge group here, the group of isometries is SL3, SL3, is basically part of SL2C. Okay, so this is basically related, closely related. I don't want to write equal because it's a real form of the thing. Okay, in any case, it just shows up. It makes it explicit. Yeah. Yeah, everything, because everything is locally ADS3. So locally, so what this statement is telling me is that any solution to ADS3 gravity, I will be able locally to relate it either to this or to that solutions. Yeah, they're all, and I'll make that explicit as we go along. But yes, that's a consequence of the statement, that there will always be some patch where you can relate any solution that you write to something that looks exactly like either of these two solutions. Yeah. So that's why I know that I solve for everything, because then you will tell me, oh, anything new that you construct is just a diffomorphism away. So that's why I was claiming victory, that I was done solving the equations of motions. Yes? What's that? No, you can always do it. It's just that it's very elegant to do it, and yeah, but I'm not. I'm lazy. Yeah. You write it like it's more convenient. You can think of it in terms of the 2 copies of SL2. There's an element of SL2 times SL2 that defines this manifold. So there's always a map between group element and the metric here. And so when you think of solutions then as quotients, you can think of them as applying quotients on the generators of SL2 times SL2. Yeah, but it's kind of more, I have to introduce more notation, and then I just had a big Brazilian lunch, so it's like, anyway, like the buffet was really interesting. So in Poincaré, it's like I don't have to introduce much notation. That's why, and in Euclidean signature, it's just SL2C, and so then I just write one thing. Here I kind of have to split it into 2 or write a 6x6 matrix. Yeah. Okay, but yeah, that's all that is going on. But like there's some papers, if you wanted references where they describe this in terms of the group elements of SL2, there's quite a few from back in the day. Okay, so yeah. Well, there's a small thing here. No, okay. No, I'll leave it at this because I don't think I'm going to use more. There's more things that you can say about how you can basically describe ADS3 as basically being the set of matrices that belong to SL2C. But what I will need for the lectures here is just that. But if you're interested in more of what goes here, and also I should say the fact that the metrics can be written in this form, oh, I erased it, is also very closely connected to the Chern-Simons formulation of the theory, because this will look like a flat connection of Chern-Simons. But again, I'm not going to use the Chern-Simons formulation much, but it's all of these pieces are at the end connected. Okay, so those are. Well, there I've written basically ADS3 in a few different ways, but you would say, okay, that's the same manifold, like I haven't really done much. So what is interesting about ADS3 gravity? Okay, so what we're going to do, we're going to play a dumb game. It will look a bit dumb, but it's actually quite instructive. And so let's grab this line element here. I'll work it out in Laurentian. And so first, let's inspect. So the first thing that I want to do, I want to set boundary conditions. Okay, I guess I will break the board. Okay. So we want to set up boundary conditions, okay? Now, there's no rule about like, oh, these are the boundary conditions. There's many, there's tons, even in 3D gravity. I am not going to be telling you about all the boundary conditions. I'm just going to fix some that were historically the ones that were first done, and it's just because they give cool physics. But if you ask me, are there other boundary conditions in ADS3? Oh yes, certainly yes. Like this is by no far unique. But let's try to play this game of like what are set of boundary conditions. And so for that we're going to inspect this metric star at r going to infinity. So we'll be at the boundary. So I should have said here. So this is basically r equal to 0. This is infinity, or Same thing for rho. Rho also goes to infinity at the boundary. So let's look at how that metric looks like when you're far away. And so this metric basically has the form. If I take it to be very far away, let me first write down what the r component is doing. So as r goes to infinity, the r part of that metric looks like dr squared over r squared. And then I have basically and I have here mine over L squared plus dot, 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 okay? So this is how the metric looks like when I'm very far away in ADS3. It is still basically, this is, if you translate r to 1 over y and do the appropriate like null directions, this is just basically ADS3. So that's why Poincaré only describes a patch of the geometry, but the global coordinates describes the whole of it. But basically, that's how it looks like. Okay? So now you can ask, okay, so let's say that I wanted to construct solutions that asymptote to this form. Okay? So I wanted to know what are a general set of solutions who, when I go far away, they look like this. And again, I'm going to ignore my statement that everything was supposed to be locally ADS3, so you would say, okay, that's clearly a solution that asymptotes to that. But let's be a little bit silly. And right, basically, so from here to here, I'm basically asking the questions are like, what are the set of solutions that asymptote to what I have on the top, okay? And so a nice set of solutions that asymptote to that form. And again, even in writing this, there's some choices of coordinates. But this is basically a space of metrics that if I take the limit r going to infinity, they will asymptote to this metric up there where x plus and x minus are phi plus minus t over L. And what tells me that this is what the equations of motion is basically nothing. So the fact that I put that these functions here, so these are arbitrary functions, or well, let me write it this way. So yeah, let me put it this other way. So let me do this. I already told you the end of the story, but I think it's better told this way. So let's say that I put here that these functions depend on both x plus and x minus. And so then if I impose the equations of motion, the Einstein's equations, then this will imply that L minus is just a function of x minus, and L plus is just a function of x plus, okay? So for any set of functions, completely arbitrary functions, L plus and L minus, these things they will solve the Einstein's equations. Exactly. There's no approximation here. You just put this in Mathematica, whatever, or you just compute the Riemann tensor, compute the Ricci scalar, the Ricci tensor, you will see this is exactly a metric that is satisfying, it's a solution to your equations of motions. Now, it looks very fancy, right? Because there's like this whole like arbitrary function here that I have parameterizing these metrics. So if you didn't know about the graviton, if you didn't know about diffomorphisms, like, or gauge symmetries, you would have said like, wow, there's tons of solutions here, right? Like I wrote something really fancy that has like all this arbitrary stuff decorating it. But this is where now we have to think about what is the physics question that we're going to ask. So how is this compatible with what we knew before? So maybe the first thing to say, before I tell you something more complicated, the first thing to note is that if I pick these functions to be 0, then I will get ADS in Poincare coordinates. And if I pick these functions to be, for its value to be -1/4, then you just have to rearrange these things there, but then you'll get global ADS3. Okay, so what? Let's erase. I think I will probably need global ADS in a bit, so I'm not going to erase it. Okay, so those are two statements that you can make. But now, let's relate to the statement that everything should be related to ADS3. Everything should be a diffomorphism. So the way that you see that, so then maybe as a third note, it's an important one, is basically to note that there's diffomorphisms that you can do. So I'll write them as an infinitesimal diffomorphisms. So you can basically do a diffomorphism and here the dots describe, I'm only writing how the diffomorphism looks as an expansion in R, but you can actually complete it. Oh, sorry, second derivative. So if you consider the diffomorphism, the way that you design it, so you don't just pull it out of like thin air. The way that you construct this diffomorphism is that you basically fix it in a way that it doesn't tamper with this. So let me call this line element here double star. So the way that you construct this, and that's why this thing has like the little dots here, because you're only wanting the metric to look like that at large R. Is fixed. So that's why that's called a boundary condition. So you don't want the space-time to change if you go very far away. You want it to look the same. So this is a diffomorphism that accomplishes that. It will not change this line. It will leave it exactly the same. But now what it does, so what it does is that it changes the values of these arbitrary functions L. And same thing for the plus. So this is how you start seeing in an infinitesimal way. So you're just doing this basically because I'm doing it in a large R expansion. You can do it by just computing here. The way that you get this is just by computing the Lie derivative of how the diffomorphism acts on the metric. And you can see that, fine, this line didn't change, but these functions here do change because of the diffomorphism. And so it means that these things at this level, at the level that we have reached in the lecture so far, it looks like, yeah, these functions, you can do a diffomorphism and change its value, so they're not really that meaningful, right? Any solution that has different values of these L plus and L minus, you can just get them by acting with appropriate diffomorphism. The only restriction that you had, of course, these functions are, again, functions of just x plus and just x minus. The equations of motions are just telling you, yeah, they're just functions of x plus and x minus, okay? So this is basically a way how you would have said, come on, lady, we got it. Like everything is related by a diffeo. This is showing to you, again, everything is related by a diffomorphism. Even though you write something that looks very complicated, it's just, again, you do a diffomorphism, you will be able to bring it. If you started with a value of L that you didn't like, so then you can just change it to whatever value you want. Okay? Great. So we're writing ADS3 and 3000. I've written to you now in like 3 different set of coordinate systems. Why are we describing the same space-time in so many different coordinate systems? Because I'm stubborn. The reason why we're writing this is because the thing that you have to question here, and this is where we were spoiled by gauge theories, is, oh, well, we were spoiled by GR itself, because GR was constructed as a theory that is diffomorphism invariant. It was constructed on the equivalence principle, right? That coordinates are stupid, right? You shouldn't, like physics should not depend on the coordinates, and the whole construction of Einstein was like, nothing can depend on coordinates, everything has to be then written in this like diffomorphism invariant way, and then he constructed this beautiful theory. But then here I am describing for you a bunch of diffomorphisms to make the point that all these spacetimes are related by diffomorphism, and so you tell me like, great, why are we doing this? And why we're doing this, the reason why we're doing this is because it was actually something overlooked. And what's overlooked here is that not all diffomorphisms are gauge symmetries. And this is important. So it's too bad that I can't erase that board. I think ADS3 will go. Yeah? Do we all know? It was useful for me. I didn't know what the Wi-Fi code was. Okay. Well, now I know what the Wi-Fi code is. Make sure you know what the Wi-Fi code is. Okay. Is there nobody? Ah, but I was sitting over there, so I couldn't see it from there. Okay. But okay, fine. Okay. The other lecturers didn't erase it, so I thought that there was something. Did you send your PDFs? Okay. 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 And so here comes basically the second portion of the strategy. So now what I did here, in this part, what I did is I basically set up for you some set of boundary conditions, and I described for you what are a general class of metrics that satisfy those boundary conditions, but all these classes of metrics are related by a diffio. So then the second thing that we have to do is basically so if you want, this was step 1, which is related to boundary conditions. Now step 2 is the observables. So how do we quantify if two space-times are inequivalent? How do we know if two space-times describe really a different physical state? This is a difficult question, right? Again, because of gauge invariance, diffomorphism invariance. Like defining mass in general relativity, right? We love to write M in the Schwarzschild metric, but if, like the first time you take a GR course, nobody really, like, okay, what's the answer? What did your professor or lecturer tell you? Why was that M? What's that? Right, it was like, oh yeah, the potential, it looks like this Newtonian potential. It's kind of like, eh. In ADS it will not work, right? Because we don't have that, like, as Kara was saying, this thing is a box. Okay, there is a Newtonian potential, but you're not going to, it's not easy to connect with a classical, like the Newtonian limit, right? And as the metrics get more complicated, this does not seem like the best way how to go. And so there's other definitions of energy. And actually, in the example sheet that I gave to you, I gave you actually 2 definitions of energy that work in ADS3. But here I'll tell you about a third one, okay, that it's easier to explain in real time. The 2 that I give in the example sheet, you just take the definitions. I give you the definitions, and I'm just asking you to compute it, so you can see that actually you will get the same values that I report here. But the way that I'm going to do it is based on the action principle, okay? Which is a more ADS CFT way how to do it, because it also relates to higher dimensions. So we basically want to quantify solutions by having some, like what I'm going to aim to do here is like my aim to define energy, and in particular, what I want to do is define not just energy, I'll define for you a stress tensor. Okay? So we had our Einstein-Hilbert term that we wrote at the beginning. And what I want to do is basically, when we write that term gives us the equations of motions, but it's not, by itself, it's not a good variational principle. Okay, so once you have boundary conditions, which is what we have here, if you go back to the action, you have to make sure that the action basically vanishes upon your boundary conditions. So you have to construct. So the first step in this construction then is in this aim is first to construct. So what I'm going to do, maybe before writing the sections, what I'm going to do is construct a good variational principle and then define charges via the Brown-York stress tensor. Which is a simple version, if you want, of Nether's theorem, okay? Okay, so let's construct a good variational principle. So we had our Einstein-Hilbert action. I won't write it again. And so there's going to be this action for 3D gravity that will have the Einstein-Hilbert part. And then I need to add, actually, in order to have a good variational principle, there's 2 terms that I have to add to this. So the first term, it's called the Gibbons-Hawkins-York term. That happens in any number of dimensions when you have basically Dirichlet boundary conditions. So K here is the extrinsic curvature. And this is the metric, or the induced metric. At the boundary, so it's basically the induced metric at the boundary is going to be, this is gamma, okay? And Dirichlet here, the reason why it's appropriate is because when I set up my boundary conditions, I wanted to hold this fixed. So gamma here is the boundary metric, and I want this to be fixed. And so that's why I need that Gibbons-Hawking-York term there. Okay? So this will assure to me, so what does this term, how many of you have seen the Gibbons-Hawking term? Few of you? Great. So what does it usually do when you vary the action? Of the derivatives of the metric, right. So then you know that the variation is just going to be variations with respect to the metric, and that's why then if you fix the metric, then it's a Dirichlet value problem. Okay, but this actually doesn't quite, so this is what you need to have a good Dirichlet value problem, but you also have some divergences problems, and so there's another term that you have to add to the saga. Sorry, let me write it a little bit. Oh, I still have G in my equations. That's great. Okay. You also need to add this counter term. And I'll tell you in a moment why you need this counter term. You know, you don't need it from the point of view of imposing Dirichlet boundary conditions. It's for another reason that will come in 2 seconds. But okay. So we have this action. Okay, so this is what's going to give us a good variational principle. Notice the term that I'm adding here does not depend on derivatives of the metric. So that's also why it's not going to violate anything about Dirichlet value problems. So I was allowed to add this just from principles alone. It's a boundary term that is compatible with Dirichlet. Okay? But now we're going to do, so this was this first step, construct a good variational principle. Now, second step, let's define this Brown-York stress tensor, okay? So the Brown-York stress tensor is basically the variation, no surprise, is going to be the variation of the action with respect to this induced metric, okay? Now, this thing you will evaluate it on shell, and what happens in gravity is that when you vary with respect to the metric and you evaluate things on shell, then of course the bulk part here is the equations of motions. So there's no contribution from the bulk part of the term, and so this thing is purely a boundary tensor. And it reflects the fact that, like, why it's so difficult to also define energy in GR, because anytime you try to construct the Hamiltonian, the equations of motions are going to tell you the Hamiltonian is 0. Oh, sorry, of 3D. Sorry, of the whole thing. Sorry, thank you. Thanks. It's a variation of the, like, yeah. So this is one of the reasons why it's so difficult to construct, basically, have a good definition of energy, because every time you try to define something, the Hamiltonian in GR is just 0 because it's one of the equations of motions, and so then it's like, doesn't work. Of course, when you have matter, like, you can use these definitions, and then the matter part of the action will give you some energy. There will be a stress tensor for matter fields, But in gravity, like, it's the equation of motion, so then you're screwed. So everything comes from the boundary, which already tells you why gravity wants to be holographic, if you want to think of those deep terms, right? No, okay. I don't know. And so what happens, so when you compute this, so I'll add these two, like, well, you add everything, and the bulk term basically doesn't contribute. And so what you get here is this quantity. So you get variations that come because of the terms that have the extrinsic curvature there. And then, so these two terms basically come morally from the Gibbons-Hawking-York term, and this one comes from this counter term that I added. Okay? And the reason why we add this term here at this level of the discussion is because in a moment, what I'm going to do is that I'm going to evaluate the stress tensor. If you evaluate the stress tensor without this term, just an ADS3, you will get infinite. And we don't like infinities. So you have to regulate that, and that's why this is called a counter term. So when we add this, this is going to make our expressions be finite. They're either going to make them trivial, or I'm going to get a number. Okay? Yeah. People are lazy, and they put the ADS radius to 1. Yeah. So in JT gravity, yeah, there's a 1 because the people like to put the ADS radius to 1. But yeah, extrinsic curvature has units of length, and so there will be some power of L. But yeah, that's exactly that term. Yes. So it's very common in higher dimensions. There's more terms that you can add, and there's a whole story of like what are possible counter terms that you can add. It's more complicated, but the philosophy is the same. In any number of dimensions in ADS, these two things are very, like, they don't change. What changes is what exactly do you write here. Like that depends on the number of dimensions. But like the principles, these are two principles that will always work. Okay? And so, great. So that's the stress tensor. And now what I want to do is basically combine this. So we have this beautiful equation here. And we have all this junk that I wrote here, that I told you this is just a fancy way how to write ADS3 with like flowers decorating it. Okay. So let's evaluate this. Let's give this guy will be triple star. And then you get a drum roll. Or you don't. Okay. Fine. No, too late. And what you see is that when you evaluate the stress tensor on the solutions, they depend on this function. What does the stress tensor compute? In life. What do the entries, what do the components of the stress tensor compute? Thank you, yes. I should have written energy momentum tensor, maybe, instead of just stress tensor. But yeah, like it has, inside of its components, it has basically the energy of a solution. For instance, the TT component of the stress tensor is the energy, right? Angular momentum is going to be like T phi. Stress is like T phi phi, right? And so what this is telling me is that despite the fact that the solutions are related by a diffomorphism, each of these solutions can carry a different amount of energy. And actually, you don't just have energy and angular momentum in this case, because basically you will have that for every of these transformations here, or if you want, well, there's different ways how to cast it, but basically you have an infinite set of charges, or let me put it this way, given how I'm writing it over there. So yeah, so let's maybe, I'll erase my triple star. So what you can show basically from here, so there's different ways how you can do this. Oh, well, there's different statements that you can make. Maybe you can chat with Robinson about this, but yeah, sorry, I'm just trying to think about which way I want to say it, because there's different ways how to say it. But basically, no, okay. I'll say it just the way that I have written in my notes. Okay, so basically from here, what we can do, so this is the stress tensor. These are the components of the stress tensor. What you can do from here is basically construct a set of charges. That morally speaking, so let me just write something schematic, just to give an idea. So basically for each of these functions here, so let me, since this thing splits into plus and minus, let me just write it, I'll write it schematically for the plus. So for any choice of that zeta plus, you can basically construct a charge, which will be the integral of Tij contracted with one of these vectors, and then times the normal. So this is like time-like normal, because the charges are defined on a surface, okay? And then integrated in this case, just along d phi from 0 to 2 pi, okay? So that basically is what you define as charge. So if, for instance, if you pick, well, you have to pick, no, let me then put it, I'll put it differently. So now, for every of these vectors here, you can construct such a charge. And what's useful, since these are arbitrary functions, you basically just decide to decompose this function in terms of Fourier modes. So this was just a function of x plus. So you basically, you can put a coefficient here, but again, charges are defined up to a coefficient. And so then, so yeah, if you want, you can put a little coefficient there, am, but they're just constants. And so then what this basically, the nomenclature then tells you is that you can define an infinite set of charges parameterized by an integer m, because here m goes through minus to plus infinity. And then the definition that you will get for the charges is that they're the integral from 0 to 2 pi. So here I was using the plus one. So this will boil down to t plus plus. And then there will be what we call an L bar. That is the integral from 0 to 2 pi of t minus minus. So you do the same thing here for plus and minus. Dx minus. And you can then write this also, of course, in terms of those L's over there. Okay? And from here, so you have basically an infinite set of charges characterized by this L and this L bar. And just to relate it to the more natural human definition of what energy and angular momentum are. So energy in this notation, which will be a choice. So to define energy, you have to look at the combinations of these two that just shift time. So that will be the killing vector that just shift times. And so this will be basically like the sum between the two, and then the difference between the two is something that will give you angular momentum. And so then energy is basically 1/2 of what I will be calling L0 plus L0 bar, and then angular momentum will be the difference. Okay, so they're just two examples of charges that you have. Okay, this is what, because you pick 0 here, they're called the 0 modes of these charges. And basically, it also makes sense because when theta is constant, is basically when you're just shifting these coordinates by a constant, which are the usual, like just energy is due to translations, angular momentum is due to to times translations, and angular momentum to spatial translations. Okay, that's the only thing. That's just what you're doing. Okay, so there you have it. What did we learn? Well, we're not done yet. Let me just maybe write down one more formula. So the last formula I want to write is that when you have charges, then the next thing, so what I'm establishing here is that you have a set of charges that are finite. So for every metric that I write, if I pick different functions here, I will have different values of these charges. But what's also very interesting of these charges, so a second property, is that they have a non-trivial Poisson bracket, which comes from like the commutator of the vectors that generate them. And the Poisson brackets of these things comma 0. Sorry. No bar there. Why did I write 38? Okay. G. Okay. And you get those two Poisson brackets between those generators. This basically here is a consequence. So the fact that you get this m cubed is because you have third order derivatives there. Okay? This part here, it's just the tensorial transformation It's just this, it's this part over here. Does anyone know what that, I know at least one person that knows what that algebra is. But yeah, this is Virasoro algebra. So the statement here, the grand conclusion, is that the classical phase space of pure ADS3 gravity by 2 copies of Virasoro with central charge equal to 3L over 2G. The central charge is basically defined by this coefficient up to normalization. So it's important here that I'm telling you now I have a classical phase space. Phase spaces are defined by charges that I can carry, okay? And then these charges have good commutation relationships, and it's commutation relationships that are known, which is basically this Virasoro algebra. So I've done my job so far. So I solve the equations of motions, I impose boundary conditions, and then I ask what are interesting observables. Now, from the beginning of the lecture, just to stress, it felt like, why did you have to go through the 2 other steps if everything is related by a diffeomorphism? So the thing that is magical in this number of dimensions, it also happens in higher number of dimensions in a different way. You can ask me how this happens in other number of dimensions. But what's interesting here is the role of diffeomorphisms in this theory. They're not pure gauge transformations, okay? There's still quite a lot to understand about how the phase space of gravity is, even at a classical level. I have done nothing fancy about quantum gravity. This is just understanding classical gravity and what characterizes solutions in classical gravity. And the fact that this, these solutions carry charges given by this gives the name, so these transformations here are called basically large diffeomorphisms. Because there are a set of diffeomorphisms that will give rise to charges. So they're non-trivial. Now, of course, you can also write diffeomorphisms that will not give charges. So for instance, you can write an expression here where, let's say that you don't turn on this term and that you put here something that goes like, oh, let me write something like 1 over r cubed. So you write a diffeomorphism that has this plus 1 over r cubed. You can do that. It's a diffeomorphism. But what you will see is that that diffeomorphism, because it decays too rapidly at infinity, it will not give you, it will not do this effect of changing the L's. It will not have an effect on your phase space. So that's why these diffeomorphisms are singled out. Given your boundary conditions, these diffeomorphisms are singled out as being physical. So they're not gauge symmetries. And they're going to be quite important when we try to understand what quantum gravity is, which I still don't know, but okay, I'll tell you what I know. And these things play a role, okay? So again, the theory will also contain diffeomorphisms that are trivial, but there's also going to be diffeomorphisms that are non-trivial, which are these large diffeomorphisms. And so the name of the game, the art here, when you're confronted with these type of theories, is to try to understand the differences between these 2 things. And again, it will depend on how you set up boundary conditions. But what this is showing to you is that, okay, at least there exists one set of, what I have shown to you is that there's one choice of boundary conditions that leads to interesting physics. So yeah, so with that, I guess we have 5 minutes. I'll let 5 minutes for questions. Is that okay? Or, yeah, you have questions? Or time for coffee? Also valid?
Okay, thank you for your talk. I'm a little bit confused in that part when you write the stress tensor in the bulk of ADS3 as the variation of the action with respect to the metric. Then you write the stress tensor as a boundary term with gibbon hogging and the counter term. But
Yeah, I'm being sloppy, but, well, okay. But whatever.
this stress tensor writes as a boundary term. It still be the stress tensor in the bulk of the ADS3, or it's the
because
stress-
it's just the bulk that doesn't contribute because you're on shell.
I'm confusing with the boundary of the ADS3
It's
and the CFT, the stress tensor in the CFT.
Oh, it is the stress tensor in the CFT.
It's the same,
Yeah.
the stress tensor in the bulk
Well, it's just that
and in the CFT.
there's no, like, okay, let me put it this way, maybe that helps you. Like, the only thing that I meant to say from here to here is that if you put an R here, so let's say that you pick mu to be R, just, and so you evaluate, like, you just evaluate this as like, oh, I'm going to vary with respect to the metric, this thing, right? And then you can just say, oh, what is the TR, what is the RR component of this thing? And you'll find that it's 0. So the only components that have support are the boundary components. Okay? Now, of course, you can evaluate this in the bulk, like at any R, and it will depend on R. But if you want, so this is general. If you want, what I did from here to here is take, maybe I should have been more clear. From here to here, I did take the limit as R goes to infinity.
Okay.
But this is still going to be true as an expression at any point in the bulk. But if you evaluate at any finite R, it will have R component, but there's not going to be an R like I component. So that's why I was kind of mixing it up with like, oh, is it the boundary metric or is it the bulk metric? Because it doesn't matter. Like, yeah. So you can just think of it in terms of like an ADM decomposition where you take the radial direction to be like your time and the gamma, the transverse ones, and then you only have support on these transfer ones to the radial one. That's,
Okay.
that's why, yeah, I'm being sloppy like that. But yeah. But then from here to here, I did take R going to infinity. So otherwise you get like some bleeding terms in R, but they're not going to, when you compute, even if you keep track of them, like, yeah, they don't do anything interesting.
Okay.
It's these finite parts that do something interesting.
Thank you.
Nico. There.
Thank you. Thank you for the lecture. So I'm just wondering, because you said that you choose the boundary conditions to be that the metric was asymptotically ADS, right? But you still have the extrinsic curvature. Isn't that part of your boundary conditions to choose?
No, I don't fix the extrinsic curvature.
But yeah, because I was thinking that how can diffomorphism change, I don't know, the charges? But to me, it's like you are changing with this type of diffomorphism, the extrinsic curvature, and that's like
No, but
somehow
the extrinsic curvature depends on derivatives of the boundary metric.
yeah. But I don't know.
But I'm not
it's
fixing
not
the-
that
but,
boundary condition.
No, I'm fixing the metric, not derivatives of the metric.
Yeah. Okay. Okay.
Yeah.
But
No,
so-
otherwise it's too constrained because, yeah, the extrinsic curvature, roughly speaking, the extrinsic curvature is something like, it will look like the derivative with respect to I of gamma ij, like
Yeah.
roughly, like, this is Kij is roughly something like
But that
this.
could be also a boundary condition. You're not fixing it, but
Oh,
it
you
is a
can,
boundary
that's
condition.
why I said, like, yeah, so right now here, the keyword is this, that I'm fixing the metric, but not derivatives of the metric. Like, then people play around with this. And so then there's papers that have done mixed Neumann-Dirichlet boundary conditions. And then the counter terms that you have to add are different. Like the boundary term, like then you don't add this, you have to do something different. You have to make sure that your variational principal is compatible with whatever variant you want to do. And then when you write, well, I erased it, but like the line element here that I had, like with the, oh, what is asymptotically ADS, then people tell you, oh no, I want to fix this, but keep this part wiggly, like, and so there's different things that you can do. There's nothing sacred at this stage of the discussion. There's nothing, like if you're just doing classical theory, like there's nothing special about this. And you will actually get charges that are interesting. They have their own properties, and they have their own phase space, and you're not going to get Virasoro. So you will change, this conclusion will change. So this conclusion here, like to be very explicit, the fact that I got here Virasoro is because of the boundary condition that I'm imposing. Okay. You change the boundary condition, you might get nothing. That's an option. Maybe you were too strict, you fixed too many things, and then nothing survives. Or you can relax them or modify them a bit, but then it will change what is the algebra, what is the phase space. So these charges here will change. You will get different commutation relationships. You will get maybe less charges. Sometimes you get more. So there's different things that you can do. Yeah. So for instance, like historically in Chern-Simons theory, the boundary conditions in Chern-Simons theory were more of the type of Neumann boundary conditions. So they let like things be more free. And they didn't get 2 copies of Virasoro. In that case, you get what's called an affine SL2 algebra. And then it was related to some fancy blocks, and there's a whole like Seiberg-Moore type thing, but okay. But it was a different phase space. Like it was a different thing that they were doing. But in any case, so you can get different things even before so this is the result of Brown and Hainaut, like even before that or around those years in the 80s, people were doing also different things. And then more recently now also people do different things. So, but yeah, but all of these things, like the conclusions are tied. So you set boundary conditions, and then that has an impact on like what are the large diffomorphisms, and then what are the charges that you get. So it all impacts each other. So they're not independent statements.
Okay, I'm a bit confused about the Virasoro algebra. Correct me if I'm wrong. Generally, a central charge arises when we can quantize the conformal field theory. Here, however, we have a central charge in the classical field.
It's very
I would like to know the difference of this conformal field and another conformal field that we don't have classical central charge. And then what's the meaning of a classical central charge?
Yeah, so this is super deep, right? Because in conformal field theory, exactly, the central charge is quantum. It has like an H bar. It's a breaking, like you had a classical symmetry, and it's an anomaly that is broken at the quantum level. I'll answer your question. You're not going to be happy with it. Because it's also, yeah, so I completely agree with you. And again, I'm stressing it a lot. I'm doing a classical analysis, and I got this result. Now, the way I understand it, and other people understand it, is 2 reasons. First, in conformal field theory, you're doing field theory. So there's a field theory statement. Here we're doing gravity, and we know this is kind of an indication, if you want, that gravity is not a vanilla field theory. Although you can treat it in many ways as an effective field theory, there's for many practical purposes, and like Julio will tell you all sorts of beautiful things that you can do with gravity as an effective field theory. This is one point where you start seeing how you depart from the theorems and laws that field theory taught you in that way. Now, from the perspective of ADS3 CFT, this is a statement, like this is telling you something about the strong weak nature of the duality. So a weakly coupled theory, which is the theory in ADS, this is the classical theory, is dual to a very strongly coupled system, which is very quantum. And so if that strongly coupled system had an anomaly, it has to be reflected on the other side. And so it's part of that, like discovering that you, like this should have been kind of an indication to you, is like there should be a dual quantum system that has these same features.
Okay, thanks.
So it's like ADS-CFT, just like, strongly coupled, like, yeah, you can't even strongly, like, yeah. So that's what's going on. But it's on, I think when Brown and Hanau wrote these things, they were surprised. And if I remember correctly, it's been a long time since I read the original paper. I do think they remark on how kind of odd that a classical system has this. Because, yeah, and then you can have objections about like, oh, these are Poisson brackets. Can you promote them to commutators? And so you can like, but okay, okay, yeah. But that's an excellent question. That's really, really, really good question. But it's again about how different quantum, like what gravity is, and then what it means to also quantize it. So it's really remarkable that we got a central charge. Yeah. And also, if you just look at the algebra of these things, it's centerless. So these guys satisfy an algebra, but they don't have an extension. So the diffomorphisms by itself don't have a Virasoro symmetry, which is fine, but the charges associated to them, they start seeing the quantum, and it's via this duality that they see the quantum. Yeah.
Okay. Question. Sorry.
Hi.
Hey.
You talk about all these, it's not variables, are like more degrees of freedom in some sense.
Yeah.
That appears from gravity, from the diffomorphisms, right?
Yes.
Yeah, so I'm thinking like in 4D, you have the local degrees of freedoms, and you should also have these large degrees of freedom, right?
It depends on, so in higher dimensions, you have to be careful. In ADS4, no.
Okay.
But if you're in flat space, then the analog of this is what's called the BMS group. So if you set up boundary conditions at null infinity, there's an infinite set of charges that you can define there. But again, it depends. That's why, yeah, there's versions of this in higher dimensions as well.
It's just that I'm thinking like, it's really strange for me, like thinking that something quantum depends on boundary conditions, like.
But look, when you, in life, like even when you're just doing like quantum field theory or like boundary conditions are never given to, well, in an exam they're given to you because they tell you solve this problem with these boundary conditions. But it's always, as a physicist, you input them. It's a freedom. The equations of motions are not going to tell you, oh, these are the boundary conditions. There's nothing. Like, and then you kind of, like, based on that, you sort of, like, follow the thread of, like, what is the conclusion that I have? Or what are the fun things that I can do? And it happens, that's not special. Like, in gravity, like, the thing is that, the thing that is surprising about this thing is that I'm giving life by doing these, by kind of, like, reminding myself that I have to impose boundary conditions. I sort of, like, discovered that not everything was a gauge symmetry. But in general, like, anytime you solve a physics problem, even in material science and condensed matter, like, there's tons of interesting things that you can do when you impose boundary conditions, when you have different sets of edge modes, and you can get layers of superconductors. Like, all of that is playing around with boundary conditions, right? Like, how do you tamper with various materials? So this is where the fun comes, like, and you start assembling new things. And that's where the creativity comes in. Like, yeah, someone gave you the Maxwell's equations and the Schrodinger equation, but then you input, like, this is a fun thing to do, right? Oh, I went to look at systems with periodic boundary conditions. I went to look at systems that have these walls, I don't know. And so that's what we're doing. And we're noticing that when you impose boundary conditions, there's fun things that show up. If you don't, then you miss it. But yeah.
That's good. Thank you.
Okay, we thank Ale for her lecture. We have one extra coffee break today, and then we have the first set of short talks given by students.